talking about process engineering of low temperature chemical bath deposition technique for flexible electronics. Yes, John.
Good afternoon. My name is Chihang Chen from Oregon State University, and this is a collaboration between my group and the group at Univ University, Professor Yu. And today I'm going to talk about process engineering of a technique called chemical bath deposition, and we try to use this for flexible electronics. So I think very well today. We talk about flexible electronics, right? For example, this is in Scientific American. I say the future look of flexible, and this is a famous image from John Rogers' group. Right now he's in Illinois, and this is E-Ink. So a lot of people working on trying to make a flexible electronics, okay, flexible display. So our goal here is to find an inexpensive process, okay, which can be used for low cost, large area flexible electronics. So there is several approach to achieve this. For example, amorphous silicon, right now is the dominant process for making a TFT display, right? And a lot of talk you heard about organic semiconductors, and it has a good flexibilities, right, and the potential for solution process, right? Low temperature, printable, spin coating, this type of process could be cheap. Okay, so what we're trying to do here different than we're taking an approach. We're trying to use compound semiconductors, okay, and we're trying to put this on plastics. So the advantage of this, it could have a higher mobility, right? In organic semiconductors, normally has better mobility than organic materials, but we like to have a low temperature process, right? So we can use to be compatible with the polymer substrate. So this slide taken from the book Thin Film Transistor from Kagan, Andrew. So you can see here depends on different application, right? Like e-paper display, the mobility you need actually might not. You don't need very high mobility. Actually, something like a 1 probably is enough. And here you can show the predict trajectory for organic mobility, as you can see, like a Penderson right now from the Professor Dr. Lee's talk. You see there's like a 5 mobility, and also there's a possibility of using hybrid materials. And in this region between below the right now the microprocessor, right, like a silicon wafer, that has much higher mobility, hundreds, so maybe even thousands. There's in between you have polysilicon, right, and what we're trying to target is inorganic polycrystalline compound semiconductor, which is in these regions. Okay, just from historical point of view, actually the first transistor being proposed, right, is actually using compound semiconductor. Right? This is a lithium field he proposed using a copper sulfide, which is a p-type semiconductors, and actually this is a mass spec structure, and it actually has a pattern. But at that time, I don't think he actually realized this transistor, but it's only a concept. But that's the first transistor being proposed, okay, in the history. So what we're trying to do is to explore a technique called chemical bath deposition, okay. So I started my career in Oregon State as a assistant professor. Okay, that's about 5 years ago, and very poor. I don't have any equipment, okay, but I do have some. A beaker, okay, in the lab. So I know a process called chemical bath deposition. Okay, sometimes I like to joke it's called chemical beaker deposition. All you need is a beaker, and you put in your solutions, and you can have thin film deposition going on at very low temperature. So as you can see, this is a beaker deposit with some sulfide semiconductors on the wall. So what is CBD? Okay, so it's kind of like a chemical vapor deposition, but it's happened in the solution phase. And it's also called chemical solution deposition, CSD. And it's kind of similar to electrolysis, but usually you have involve two reactants, okay? And you can the thin films produced from the surface reactions, and it involves similar mechanism like a CVD. You have mass transfer reactant, absorption, surface diffusion, reaction, desorption, nucleation, and growth. And possible to prepare film at very low temperature. Normally it's below the boiling temperature water, like 100 Celsius. And it deposit on any insulated substrate. So from a historical point of view, actually it's quite a very old technique. Okay, actually it was first reported in 1884 by John Reno at more than 100 years ago, right? And was used to make a lead sulfide photoconducting detector around 40s. And first report cast sulfide deposition by a group, I think by this person in 1961. And following that, there's a very good a group in Russia. They do a lot of fundamental study of this process. And then later on, people extend this. They replace the cyurea to a selenium source, so they can deposit the selenites. Okay, for example, like cast selenites and selenite compounds. And there's after that, there's a French group. They do a very good fundamental study. They propose a molecule by molecule growth mechanism for the cadmium sulfide, and that's right now most of the accept mechanism for chemical batch deposition of cast sulfide. And many common semiconductor systems like a 2,6, 4,6, 5,6, or 1,3 can be deposited by this technique. So I tried this first using the cast sulfide. The reason is cast sulfide is very the growth mechanism is very well understood, and I actually had experience with this process for thin film solar cells. So I use this, and there's two mechanisms. First is homogeneous particle formation. Actually, what happens is you put in some cadmium chloride salt, and that dissociate. You have free cadmium ions, and you put in some complex agents like ammonias, and this complex agent will complex with the cadmium ions, and then you put in a source, sulfur source, in this case cyurea, and they decompose into a free sulfur ion or HS. And this, you could have this, once you reach the saturation limit, you can have particle formation, and this is kind of like a precipitation process. Okay. So in the same time, you also have another mechanism, which is heterogeneous film growth. And that is more like a CVD process. You have cadmium, okay, it's complex with ligands, and they go to the surface, and then they have some kind of area with the hydroxy group on the surface. You have cadmium hydroxide. Then the sulfur source come in, and you have this bigger complex molecule and decompose, and you get your cadmium sulfide thin film, and you have a new site for growth. Okay. So I'll just show you a cartoon. So you have this substrate. You have some free cadmium ions. You put in a complex agents, and they complex with the metal ions, and you also have the sulfur source, which can dissociate, give you a free sulfur ion, and free cadmium ion, free sulfur ion give you the nanoparticle, and the nanoparticle can stick to the surface. Okay, so you have nanoparticle film. At the same time, you also have the surface reaction. You have the cadmium complex assault to the surface and go through a serious surface reaction, and you get cadmium sulfide film. So this process, actually you have two process competing. Okay, you have this surface like a CVD type of process, but you also have this homogeneous process like a particle sticking. Okay. So what kind of film you get from this type of process? Okay, so essentially this is quite a low-cost process, a cheap process. So what you get, this is TM image. You see these are actually nanocrystalline film, and it's normally this is shows a hexagonal cadmium sulfide structure. So essentially, what you get from this process is nanocrystalline thin film. Okay, but amazingly, actually, you can get epitaxial growth. Okay, although this is quite a cheap process, if you put in a single crystal substrate, okay, if they like a 111 indium phosphide, then you can grow epitaxial cadmium sulfide film on the indium phosphide, okay, at very low temperature. So what we did is just try this kind of film be make a transistor. Okay, so we just use a simple test structure. So we put on cadmium sulfide. So we're using highly doped silicon as a gate, inverted gate structure essentially. So you have put on source and drain. As you can see, this optical image. This is 20 micron transistor to 40 micron transistors. Okay, And so normally first we find we need a little bit of kneading, okay? So we try to do the kneading not high temp, but try to do it compatible with the polymeric substrate we use. Okay. So for example, we do 200 C annealing. You can see improve the conductivity quite a bit, and that's within that's. I will talk about this how we try to engineer process. Okay. So essentially, you do a vacuum anneal so we can get a transistor, and the behavior like the transistors, and we found when we plotted transconductance, okay, and we found there's actually operate in two regions. One is in a depletion mode region, and the other one is accumulation mode region, and the mobility is about around 1, okay, like 1.25 if it's operating accumulation mode. And this is the first pass device we tried using this process. So I will do some tweaking of the process, and we can get quite nice device performance. On-off ratio about 10 to the 6. The mobility usually is between 1 and 2 for this process. We also try to make it flexible. Okay, so what we got is we can get the field mobility about around 8. Okay, from this CVD CDS film. So this shows a typical experiment setup for the chemical bath. Essentially, just need a beaker, so you put your substrate in there, and you have a hot plate, and then you start your reactions. And as you can see, this shows a growth curve. Okay, so this is from the quartz crystal microbalance, and this is a time. As a function of time, you can see actually there's about 4 regions. Okay, so first is the induction region. Mostly probably related to the absorption. It takes some time for the reactant to go to the surface. So at this time you don't see much growth. Then you have a linear growth region, which is more of the molecular level growth. Then suddenly you have a much faster growth, and that's related to you form a lot of particles, right? Then the particle stick to the surface, so that's why you have much higher growth rate. And since it's a batch process, right? So once the reactant will deplete, then stop the growth, right? So then you can see this start to slow down and stop. Okay, so this is typical what you see in a batch CVD process. Okay, so we try to do some fundamental study on how this growth was study the growth mechanism. So we do some for example, we do an AA measurement, and we follow the cadmium concentration. Okay, so this is the growth curve, and what we see is. It's not surprising, right? The cadmium concentration drop, right? As a function of time, when the growth is going on, and you have more and more particle formations, okay, in the solutions. Then we use some. There's a growth mechanism model published by the French group. So we use this model essentially just try to reproduce and see if this model matches with experiment data. So we use their reporting K value, okay, the reaction constant, and that fit pretty well for this linear growth region, okay. And since there's a molecular level growth model, right, so it didn't take into account the particle formation, so it can only describe this region. But what's surprising us is actually we found out that from the model, right, our major total concentration actually dropped much faster. This is predict. If you see the model, right, what you find is the concentration doesn't change much because they didn't take into account the particle formation. Particle formation also consume the reactant. So actually, this doesn't fit to our data. Okay. So what we think the discrepancy, okay, most likely is the growth model fit with the growth rate very well, but the concentration data doesn't fit well. So what we think what's going on is you have a mixed growth mode. Essentially, you have molecule by molecule, and also you could also have the cluster by cluster growth at the same time, or at least there's a particle formation which consume the reactants, but that doesn't take into account into their K value. So although the model fit well, but the K value might be wrong. Okay. So just to show this, so we follow this dynamic light scattering. So we found that once you mix the reactant, okay, in a short time, within minutes, you start to see a particle formation. Okay, and that's showing the particle, nanoparticles forming in the solutions. So this just shows some. This is we take, for example, if you take the solution out and just drop the solution and put that on the, for example, silicon substrate, you can see these are after the solution dry. You see this is cyurea. That's kind of interesting. This is actually means the cyurea is not being consumed initially, right? So then when the solvent gone, you have this cyurea crystallized. Okay, and you can see very small. Actually, these probably some of the cadmium sulfide. As a function of time, you can see this cyurea kind of decreasing, right? Because you're using the sulfur source, and the cadmium sulfide is growing, right? After 10 minutes, you can see a lot of cadmium sulfide nanoparticle is forming in the solutions. And so the implication of this, actually, the particle formation is not good for the device performance, right? As you can see, sometimes you can have particle forming and they stick to the surface, right? And it's not going to do good if that's on your channel layer. So what we need to do is we're trying to develop a new experiment technique, because in this case you have both homogeneous particle formation. You also have heterogeneous surface growth, right? So since you have these two all together, but if you're just using conventional batch process, right, you could not separate these two reactions because they're always going on at the same time. Okay, so what we want to do is we want to change this reactor and try to produce a flux, okay, which we can control the particle size and their distribution, right? Or maybe we can just get rid of the particle in the flux, so we can have only molecular level growth. Okay, so the approach we are taking to do this, essentially we change the batch process to a continuous process. Okay, so we just use this is just two syringe pump, and we use micro mixers. This shows the micro mixers. And so the two reactants go through a mixer, then they go through capillary tubings, and this tubing we can control the temperature, and we can control their temperature before they impinge on the substrate, and the substrate can be heated, okay, to certain temperature. And so in this case, so we can control, right? For example, you can control the length of the tubing, then you can control the resonance size distribution, and you can control the homogeneous flux. Okay. So the micro mixer we use is made by is from the IMM in German, and this is micro mixer. Essentially, you have two reactants, right? Two inlet go through, and here you can see some small chips, and this interdigital micro mixer. Then the two reactor mix, and they go through the outlet, and the outlet go through the temperature control bath. So you can see in more detail. This is the microstructure of the mixer. Essentially, you have one reactant go through this one set of interdigital channel, and the other set go through another side. Okay. So how they work as a mixer. Okay, so essentially you have two reactant comes in, okay, and they go through the interdigital mixer. So you essentially slice your fluid, right? So they become very thin layer. So that help your diffusion, reduce the diffusion length. So that makes your mixing faster without using servos or anything, something like that. Okay. So just show some result we got from this using this reactor. Essentially, if you just use a batch process, this is a 2D surface profiler. The roughness is much rougher, right? As you can see, a lot of spike on the surface. But if you're using this, we call it continuous flow microreactor, what you get is much smoother film. Just use some AFM image, okay, of the film produced. This is one produced from the microreactor. As you can see, what you get is a more continuous, okay, and I think this is because the concentration of flux is constant and higher, and so you have much higher nucleation density. So you get a continuous film. If you do a batch, actually within the same time, that's about 3 minutes. You get actually, it's kind of neat, but you don't like this for your device, right? Because these are more discontinuous nano dots, right? These is about few hundred nanometers, something like that, right? These large cadmium sulfide nanocrystal. Okay, so if we do the deposition a couple more times, if we deposit this on the silicon substrate, and what we find is using this impinging flow reactor, actually we got very highly oriented film. Okay, this is 111, this is 222. Okay, and this is very low temperature. This deposition is only happening at like 50, 60 Celsius. Okay, and this is from the silicon substrate. And it's a cubic cadmium sulfide. So to show some this just to show the SPS and show just like a typical chemical CVD deposit film is has cadmium signals, sulfur. Usually you have a little bit of oxygen because this is you just do this outside in the air. So normally that's what you have, and some of the carbon that's common for the film which is not depositing in a vacuum. Just to show, so we took some. This is a TM grid. Okay, so we collect the solution from the flux. What we want to do is we want to reduce the particle, right? So essentially, so in this slide, actually you can see that we didn't find any particle. Okay, if you just collect the flux from the impinging flow, essentially we show there's no particle formation using this approach. And but if you keep there for a longer time, and you can see this. This is a lacy carbon grid, and these are nanocrystalline cadmium sulfide deposit on the lacy carbon. Okay, they are not as highly oriented as the one on the silicon coupon, but because I think they don't like to grow on the lacy carbon film. But essentially, it shows the particles form more through a molecular level growth. Okay, instead of particle sticking, right? Because in the flux, actually, there's no particle forming. And in contrast, right, if you just took some of the solution from the batch process, okay, and you put a drop, okay, on TM grid, what you see is you actually see a bunch of small nanoparticle, okay, form in the solutions. Okay, and this is some high resolution TM image, and so essentially, if you're doing a batch process, within the same time, your batch is already had a lot of particles, right? So those particles can just go and they stick on the surface, and that's not doing any good to your device. Okay, so this just to show the these are actually let me see. Yeah, these particles forming the solution is more like a cubic cadmium sulfide nanoparticles. And just show some EDX. Essentially, you have cadmium and sulfur. You have some residual chlorine from the solution because we use a cadmium chloride source. Okay, so what we did is, so we test this, we use this film, okay, deposited by these reactors. And the only thing I want to point out is after we deposit, we didn't do any post-annealing. Okay, we just want to see if this can improve the device performance, okay, and also reduce the processing temperature. And we found we actually can make functional transistors. And although the mobility is slightly lower, it's about 0.45 in this case. But we're quite happy. We think if we tweak the process a little bit more, we can get very good, much better device performance. Okay. So the future world, we're trying to modify the reactor, and I think we need to make it better uniform flow distribution and temperature control. And although we picked cadmium sulfide as our test case, but as you know, cadmium is nobody likes cadmium. Cadmium is a bad thing to have. So what we want to do is, since we developed this process, we try to use it for other. Let me see. Actually, I was talking about the next one. Actually, we want to try other semiconductor material, for example, oxides, which is maybe more environmental friendly and maybe more higher bandgap material, so we can have transparent transistors. And we also want to use this to make a flexible transistor and maybe other semiconductor device like solar cells. So just to show some of the progress in this future direction, we actually make some metal oxide thin film transistor using the microflow this reactor. And actually what we got is we didn't do any post-annealing for this, and the deposition time is about 2 minutes. And we got mobility, which is I think it's pretty good. With this low temperature process, we got about 2.1 mobilities. Okay, and the on-off ratio is more than 10 to the 4th. And this is just a first pass process. We didn't do any tweaking of the process. Another thing we're working on right now is try to make nanostructural film, maybe porous film, using the particle flux. Okay? Essentially, we can use the micromixers, and we can, instead of generating a flux-free, particle-free flux, we can actually generate particle flux. Okay, so we can use the particle flux and impinge on the substrate, and we can use them to make a nanostructure film. And we actually see, if you're using a micromixer approach to make nanoparticle, actually you get much uniform distributed nanoparticles. And actually you can also tune the process, right? You can tune the particle size by controlling the residence time of the process. Okay, and finally, I'd like to acknowledge this funded by National Science Foundation through career grants, and also the electrical photonic device program divisions. Okay, thanks for your attention.